Okay, so hi everyone. Welcome to today's session. So after two sessions of the decoders, in this tutorial, Kishor will going to explore the more fundamental question, like which quantum codes are actually possible. So the tutorial will answer this in two parts. Like the first part is the theoretical limits. We'll go through the Singleton, Hamming, and Gilbert Varshamov bound. And for the real physical limits, we will cover the I'm sorry, maybe I'll pronounce this incorrectly. Bravyi, Poulin, and Terhal bound. I don't know if it's correct. Yeah, and this will show us like how the physical layout of our device limits the codes we can build. So let me hand over to Kishore to begin today's session. Okay, thank you,
Yeah.
Kishore.
Okay. Yeah. Perfect. So yeah, I mean, if there are questions, I mean, please ask, and maybe I will start. Okay. So a lot of content will be from the book by Daniel Gottsman called "Surviving as a Quantum Computer in a Classical World," and some content from like the papers which are on internet. So so let's say n is number of logical qubits or qubits that we are working with. Okay. Let's say capital K here. Capital K is the dimension of the encoded subspace. So you have a code space, and let's say its dimension is capital K, which is, let's say if you're working with qubit of dimension q, then it will be q to the power small k, where k is what people call number of, uh, uh, yeah, sorry, number, n was a number of physical qubits and not logical qubits. It was physical. Yeah. and and then let's say you have a small k number of logical qubits or qubits, then the dimension of the encoded subspace is small q to the power k. And let's say d is the small d is the distance of the code. So these are the parameters. Then you might be interested in a small k by n, which is encoding rate, and let's say distance by n, which is called distance rate or distance. And basically, encoding rate tells you how well you can store information, and distance tell you how well you can fight against, like noise. Like, I mean, like what is your noise tolerance? And you can't have everything. Like there is a fight between them, like between these two. So, so that's the tussle. And one can ask a question that, let's say, given n physical qubits or qubits, let's say I've taken q, and dimension of the subspace capital K, which can be, like q to the power small k, like, I mean, uh, where q can be 2, then it's 2 to the power small k. And these the distance, given these parameters, does a code exist with these parameters? Somebody can ask this question. This is a very useful question. Like, I mean that can cross someone's mind. I mean, let's say they are trying to design devices, or like some error correcting code for their device, and they want to protect it, and they are maybe interested in particular kind of code. And this problem is extremely hard to solve. But I mean, not all hope is lost. You can find some bounds. Like you can say that maybe codes with certain parameters are possible above and below. So you can bound things. So you cannot, and maybe you cannot say that whether a code is possible, but you can definitely rule out what kinds of codes are not possible. So, so yeah, I mean, that's more on the, I would say, on the side where you won't look for, like those kind of codes which are not possible. Uh, if let's say bounds do not allow for such codes. So bounds are good. I mean, they tell us what kind of codes are, not possible, and tell us, like what is the range or regime where we should look for codes. So I hope everybody understands the question. I mean, the question is that, several people are interested in is basically given some parameters, does a code exist or not, which is hard, and we cannot answer it. So we try to find some bounds. And indeed, we will look at a few bounds. We will have a few bounds, and we'll try to make sense of them. So if you have questions, please stop and ask like at any point. I mean, if it's clear, it's okay. But the goal is to not cover things, but like to uh, convey some of the ideas. So the first bound that one can discuss, this thing called quantum singleton bound. Okay, this is called quantum singleton. Quantum singleton bound, it comes from like classical singleton bound for classical code. And this bound basically says, there's some detail here, which I will share the slides later and you can read it. But what it says that n number of physical bits minus number of logical bits is greater than equal to d minus 1. That's what it says. So it basically says that k has to be less than equal to n minus d plus 1. So if you increase your d, k will decrease. So higher protection means smaller encoding rate. Like that's what it tells you. And in quantum case, like in the quantum singleton bound, you have the same thing, but with a 2 in front. So one might think, why do we have a factor of 2? Yeah. And actually, you will see this kind of factor of 2 like occurs quite often when we look at the classical bound versus quantum bonds. Okay, so this is your classical bond, this is your quantum bond. So this factor of 2 that you have here, it turns out to be the no cloning theorem, which is surprising, right? But I will give you a proof and convince you that it is indeed no cloning theorem. Like it's no cloning theorem that leads to this factor of 2. And you can think of this singleton bound as a way of codifying just how well information can be spread around without accidentally repeating anything, because like if you repeating is not possible, like that's what like no cloning theorem says. So you can spread information around, but you cannot repeat them, because if you can repeat, then let's say if you can recover from it, then that will violate no clone. What I'm saying, it will make sense. But so just like you can remember it even if you forget about singleton. What you can see quantum single, you can remember that there is a factor of 2 difference between classical bond and quantum bond, and that comes from no cloning theorem. Okay. By the way, a historical fact I would like to mention: everybody gives credit to singleton, but this was earlier proven by Joshi in 1958. So maybe it should be called Joshi bound. But Joshi notes that the result had been obtained by Komamiya in 1953. And there is a later work by Welch that also says that also notes that it was Komamiya. So maybe we should call it Komamiya Joshi singleton bound, instead of just singleton bound. Like everywhere in the books and so on, people call it singleton bond, but it's better to call it, like I don't know, quantum Joshi Komamiya singleton bond, because it was like Komamiya first, then Joshi, then singleton. Okay. So quantum singleton bond, by the way, like you don't need to maybe call this all that. You can just call it Neil Lafla, because it was Neil and Lafla who discovered. But the classical version, it was discovered by Komamiya, and then Joshi, and then singleton. Okay. So let's say, for general K, proving is more, the proof is more involved. But I want to give the insight that it's no cloning theorem which is responsible for this factor of 2. So I just take K equal to 1 here. Okay. And And I will show you that, like this factor of 2 comes because of, no cloning theorem somehow, can be used to prove this result. So let's say there is a code that has a distance d, then it can correct d-1 erasure errors. Okay, that that we know, we have heard in previous sessions or something. So let's say you have n registers, like you have n qubits, like state psi. So what you do, you take your n registers and like you break it into 2 parts. Like you have set A with d-1 register and set B which has n minus d-1 registers. So 2 parts, like one has d-1 and the other has n minus d-1. Okay, we break it 2 parts. Now note that set B has n minus d-1 registers, which means B has suffered d-1 erasures. So from B, you should be able to recover the original state psi. Okay, makes sense? Now let's assume that this relation is not satisfied. So then we will say that this n minus 1 is strictly less than 2 times d-1. Okay. But then that implies that I can get rid of this one, and because these are all integers, n is less than equal to 2 times d-1. Okay. And then n minus d-1 is less than equal to d-1. So what does this say? Which says that set A, which has d-1 registers or qubits, has suffered at most d-1 erasures, because d-1 is greater than equal to n minus d-1. Okay. So using A, one can reconstruct psi again. And then using B, we had reconstructed psi again. So you divide in 2 parts and you can reconstruct psi and psi. So this can be a very nice scheme. Like I have this, such an error correcting code exists. I take my psi, I redistribute in A and B in this manner, and then from there I reconstruct my 2 copies of psi. So I start with 1, get 2 copies, and this should not be possible. So we may somewhere be assumed, like something which has to be wrong, and it is here. Like if you go back by contradiction. So this has to be n minus 1 has to be greater than equal to 2 times d-1. Okay. So this is a very simple proof of quantum singleton bond for k equal to 1 case, and this factor of 2 comes because of no cloning theorem. I hope everybody can appreciate this. And take a moment to appreciate it, and then we move to the next one. If anybody has any question, please ask. Else, I think just remember that this factor of 2 is, no cloning theorem. Okay. No question. So then we can prove that there is no 413 code, because I can take n equal to 4, k equal to 1, d equal to 3. Now, what is n minus 1? N minus 1 is 4 minus 1, which is 3. 2 times d minus 1 is 2 times 3 minus 1, which is 2 times 2 equal to 4. This number should be greater than equal to this number, but that is not the case. 3 is not greater than equal to 4, which means there is no 413. So using a simple argument, we ruled out a certain code. So one can ask, there are codes that saturate the quantum singleton bond, and these codes, motivated by in the classical world, they are called maximum distance separable, or MDS code. And 513 code is one such example. Like for 513 code, you can calculate this thing and the bond is exactly saturated. So 513 code is a quantum MDS code. 422 code is another such example. In fact, n minus 22 code for any even n is a MDS code. Okay. So this completes our discussion of quantum singleton bond. If you have any question, please ask. else I will move to quantum Hamming bond. Okay. So we studied quantum singleton bond. Okay, there is some question. Somebody has raised their hand. Maybe unmute and ask. Yeah.
Yeah, so for the second one, that is for any even n,
Yeah.
yeah, what's the reason why is n supposed to be even?
I mean, you can try it for odd n, and it won't be saturated.
Oh, okay, but it
Yeah.
can be a valid code.
Yeah, I mean, maybe, I mean, you have to try it. I mean, I have not tried myself. I mean, here you
Okay,
have the relation. Here you have the relation like this
okay,
n minus k 2d minus 1. You put those numbers. Okay, let's try. So what do we have? We have n minus 2, 2.
yeah,
So what is n minus k?
n
n
minus k
minus
is 2.
k, n minus k is 2. And n minus k is what? Yeah, n minus k is n minus 2, which is 2. And that is greater than equal to 2 times d minus 1. So that is like 1. So 2 is greater than equal to 2. So one can say that this seems to hold for any n, right? Yeah. Yeah. So there may be, okay. So the claim is that this holds for any even n. I'm not claiming that it does not hold for odd n, but I believe there must be some other reason, like some other bound or something. Like let there be some other way, like one maybe those codes do not exist or something. I don't know. Like yeah.
Okay,
I mean, for example, this one, right? I mean, okay. So let's try 312 code. Okay. So 312 code will be, yeah, I mean, yeah, it will saturate. But I think you can show that maybe I think this in the linear programming bound later, one can prove later. I think it comes later that there is no 312 code or something. I mean,
okay,
have I written it here? Okay. Yeah, maybe you can like look at this book by Daniel Gottsman. Uh, like you can, I mean, first of all, the code has to exist, right? I mean,
mm-hmm.
uh, to say that it saturates the bound. So for even n, like I mean, we are showing that it saturates. For odd n also it seems to saturate, but maybe there is some other way through which you can show that such a code even does not exist.
Okay, okay, okay. Thank
Yeah,
you.
like it's
Thank
like an upper bound, but the upper
you. Yeah,
bound may not be an achievable bound,
mm,
right? I mean,
yeah.
okay.
Thanks.
Yeah. So that was singleton bound. Okay. Now let's look at Hamming bond. Okay, Hamming bond. So this bond is also known as sphere packing bond. So Hamming bond basically says that, let's say K is basically size of your, like code space times Q minus 1 to the power j, n choose j should be less than equal to size of the entire space. Now, how do we get this number? I mean, actually, I will give you a sense of that. And in a quantum Hamming bond, you get again a factor of 2 difference, but 2 now comes in the, in the power, right? And basically, like what we are saying, that let's say if your code corrects for t error, like let's say, then the distance has to be 2t plus 1. And that's why in the summation, it goes up to t. Like I'm giving you intuition, like why do we have this bond in this form? And we are saying that, let's say you have j errors. So the j errors can happen at j places. And let's say we are working with, like, uh, I don't know, like, I mean, uh, alphabet of size q, then there are q minus 1 possible errors that can happen. And you are just counting all possible errors that can happen times the, like the size of your code space, it should be upper bounded by size of the entire space. In the quantum case, you have more ways in which your errors can occur. So let's take Q equal to 2. Then 2 square minus 1 is 3. So you can have X error, Y error, and Z error. On the other hand, here you have just 2 minus 1 is 1. So in the classical case, you have for Q equal to 2, you have just bit flip. But for Q equal to 2 in the quantum case, you have 3 errors. So this factor here, the 2 that you are getting, let's say again the difference of 2 that's coming in the quantum case, is because of the number of ways in which error can occur in the quantum world. I mean, so again, maybe you can just remember that there is a factor of 2 difference, but this time it's sitting in the power. Okay. Now note that this upper bound that we have in the quantum Hamming bound, it holds only for non-degenerate codes. Okay. And while we don't know how to prove that this Hamming bound applies to degenerate code as well as non-degenerate code, we also don't know any example of a code that violates the bound. So this is an open problem. Like to show that, I mean, I will later say that, like this, in fact, I will talk later that this quantum Hamming bond for degenerate quantum codes, it will be a big theoretical breakthrough. Like if you can solve it. So we don't know whether, in fact, I was watching one of those QIP, like videos where people interview different researchers. And in one of the videos, I think they interviewed Daniel Gaussman, and they asked him like what he had expected that did not happen. And he said that he thought that quantum Hamming bounds proof for degenerate code will come out, but so far it has not come out. So maybe someone in the audience can do it here. Okay, so let's go through, like this quantum Hamming bound and this. So let's take Q equal to 2. So this capital K is 2 to the power K, and that's how it looks like. So this is the size of your code space, and then n choose J says that like you can have error at J many qubits in these many possible ways, and which qubits can get corrupted. So which qubits can get corrupted? The way you can choose that in n choose J manner, and then 3 choose J basically tells you, the number of possible ways errors can happen, like X error, Y error, or Z error. And you multiply that with this code space, and that should be upper bounded by the size of the Hilbert space. So that's what Hamming bound basically says. And a perfect quantum code is a code that saturates the quantum Hamming bound. Okay. Yeah. Oh, by the way, I need to give you the proof of this quantum Hamming bound. Okay. So let's look at the proof of the quantum Hamming bound. So for that, first look at the quantum error correction conditions. Correcting code conditions. So if you remember these Neal-Laflamme conditions where you have, let's say, some code word psi and phi, and you have some error EA dagger EB, then psi EA dagger EB phi is CAB psi phi. This is your Neal-Laflamme condition. And the good thing is that this CAB, it does not depend on psi or phi. In fact, C is a Hermitian matrix. This is your Neal-Laflamme condition. And what happens that in the degenerate code, so in a non-degenerate code, different errors will produce different syndromes. But in degenerate codes, different error can produce same syndrome, or different error, like the way they will act will be same. So for example, let's say in the Shor 9-qubit code, if you act on, let's say, by Z1 or Z2, the result is same. It does not matter. So different errors, but same result. So what happened that in the non-degenerate code, where different errors have different result, the C matrix that you have here, it is basically full rank. And we will use this fact to prove the quantum Hamming bound. So this is your quantum Hamming bound. Now let psi is perpendicular to phi. So you have this Neal-Laplam condition, and let's say psi is perpendicular to phi. So then psi EA dagger EB phi, that has to be 0 because we have here overlap between psi and phi. Okay, and because psi is perpendicular to phi, it will be 0, which means EA psi and EB phi, they are perpendicular for all AB. They are orthogonal for all AB. So if you start with a bunch of psi I, which are basis for the code space, this EA psi I for all A and I are basically linearly independent. And they will together fill the entire space, the Hilbert space. So yeah, I mean, that's what we are. So now after that, you just do the like counting argument. So let's say dimension of the code space is capital K. Let's say number of one qubit error that you can happen is like q squared minus 1. So let's say for q equal to 2, you have 3 possible errors, x, y, and z. So the number of linearly independent errors of weight up to t, you can count will be n choose j q squared minus 1 power j. And these are like a number of different errors, and you have to multiply that with like a number of different code words. So you have these many errors, and you have, let's say, psi I many like code words, linearly independent. So you just multiply k times b, and that k times b has to be upper bounded by size of the Hilbert space, which is q to the power n. So it's just a packing argument that you do for non-degenerate codes, like, because we assume that C is full rank, and using that basically we did this counting argument. But assume that C is not full rank, and then can you have some kind of a bound, like, which you can call Hamming bound, and a code that saturates. So let's say here I have written the quantum Hamming bound for q equal to 2 and k equal to 2. So for q equal to 2 case, it looks like this. And a perfect quantum code is a code that saturates the quantum Hamming bound. So let's look at 513 code. So this code is very beautiful. Just now we saw that it saturates the Singleton bound. But if you take t equal to 1, d equal to 3, n equal to 5, you can count these numbers, and like these things, when you calculate, you get 32, and right hand side is also 2 to the power 5, which is 32. And because 32 is less than equal to 32, this code is a 513 code is a perfect code. So it's an MDS code, it is a perfect also. But 713 code, when you calculate n equal to 7, k equal to 1, and d equal to 3, the same thing, your left hand side is 44, and right hand side is 2 to the power 7, which is 128, which means Steen code is not a perfect code, which means there is a lot of wasted space, if you can say. So in a Steen code, the way the code words are packed, there is a lot of wasted space in Steen code. But in quantum error correction, in the stabilizer codes and so on, we know, we have so many degenerate codes. So these codes are degenerate code, and that's why there is a lot of wasted space. If one can go by this quantum Hamming bound argument. So I don't know. Maybe there is a tighter bound than quantum Hamming bound for degenerate codes, but that is waiting to be discovered. Yeah. So this is a major open problem that one can
I
work
have a
on.
question.
Yeah.
Yeah. So you're saying there could be a tighter bound, but even the seemingly loose bound we haven't proved yet, right?
Yeah.
Like,
To my understanding, we haven't found a violation.
right. We don't know of a violation, but we also haven't proved that just the basic Hamming bound applies universally to degenerate codes.
It will apply to degenerate code, right? It will, because what we are saying is that we are it's an upper bound, right? So just that when you are assuming non-degenerate codes, you are like giving a loose upper bound basically. But if you take into account, because I mean, here you are doing this counting argument, right? Like here there is counting argument, and we are saying that ESI, AI are linearly independent. Now for degenerate codes, that may not be the case. Like there will be some factor or something will come up, and you will have a tighter bond. But what I'm saying that tighter bond will mean that your upper bond will become lower. like you will
Right.
you will bring
But
it down.
when you mentioned earlier about the open question, can you repeat like what exactly is open?
So open question is basically quantum Hamming bound for degenerate quantum codes. So that will be like, so I can show you, like what I mean. So here is your quantum Hamming singleton bound, and there is a quantum Hamming bound, and I think actually maybe I think you will have to make it a bit, like tighter or something like that. I don't know. Like it will come down a bit, yeah. I mean, does that answer? I mean, it's an upper bound, so you want to make it a bit tighter, which means you want to bring it down a bit.
Yes, I am a little confused. Sorry, but I don't want to deal
So
stop.
I mean, basically, what I'm saying, like Varun, is that that here, like this is the argument, right? I mean, that we are saying that all
Sure,
these are
sure.
linearly independent, but that will not be the case.
That will not be the case.
For
No,
the
but my
degenerate
question is, so that means that even this upper bound, which empirically seems to be loose for degenerate codes,
Yes.
we haven't proved it for the degenerate case, right?
Yeah, like we haven't proved that, like I mean, wait. True. Yeah. Sorry, maybe I say it in a wrong manner. Like maybe for the degenerate code, it could be possible that your encoding rate can be higher because you are able to pack more with the same distance. Yeah. So we haven't proved that, I mean, so we have to find a degenerate code because non-degenerate code will respect it. Degenerate code can violate it. Yeah. Sorry. I think I said it in a wrong manner. Yeah. Degenerate code can violate it. Yeah. But we haven't proved. I think we don't have an example of a degenerate code, if I'm correct, which violates the quantum Hamming bound, which was proved for non-degenerate case.
Okay, thank you.
Yeah, sorry for the confusion. Okay. Yeah. So yeah, I mean, I don't know. Maybe one can take into account some matrix rank or something, but yeah, that will be a bit complicated. But I think it will be good to prove some bound, like quantum Hamming bound for degenerate codes. Okay, so now next is quantum Gilbert Varshamov bound. So far we talked about, like I mean, we said that encoding rate will be less than equal to. So we were giving an upper bound on the size of the code space, right? I mean, it was like k less than equal to kind of a relation. But now you can give some kind of a lower bound. And this lower bound, we say that certain kind of codes are possible. Like this is more like a hopeful scenario where you're saying that, so that upper bounds are saying that codes of certain kinds are not possible. You are ruling out. But Gilbert Varshamov bound is giving you a lower bound saying that certain kind of codes are possible. Like it's a lower bound. And the Gilbert Varshamov bound basically it says that let's say this is your size of the code space, like in their notation, which is like capital K for us. Or in the classical case is written like K n choose J Q minus 1 to power J. So you remember that earlier we had J equal to 0 to T. Now we have J equal to 0 to T minus 1. So that is the difference. Like, I mean, if you want to contrast it against a quantum Hamming bound. And yeah, you can write it for q equal to 2. That's how it will look like. And this is your size of the code space. This is like a number of type of errors that you will have. And this is the size of the total space. In quantum case, you have just a factor of 2. So here you have q and you have a factor of 2. So in all three cases, like Singleton, Hamming, and Gilbert Varshamov, there is a factor of 2 difference between classical and quantum. And this factor of 2, like in the Singleton bound case, appears as multiplicative factor, and in the Gilbert, Varshamov, and Hamming, it's in the exponent. So that's an easy way to maybe like remember it. Yeah. So for q equal to 2, this is how the bond looks like. And for large n, I will not go into detail, one can prove that the rate, your encoding rate, has to be 1 minus dy n log 3 minus this factor, which is entropy, binary entropy, h dy n. And you can put a value of you can put some constant dy n here, and still this bond is satisfied. So for some constant r, what does this mean? This says that for constant r and constant dy n satisfy this equation. And the codes for which you have constant encoding rate and constant distance rate are called good codes. So Gilbert-Varshamov bond guarantees the existence of good codes. So this is your hopeful scenario. Like, I mean, why should we one even like look for good codes? Because such codes are guaranteed by quantum Gilbert-Varshamov bond. So later, when I will talk about, let's say quantum LDPC code, I will talk about something called good quantum LDPC code. And one can say that, Gilbert-Varshamov bond kind of guarantees that, like maybe there are some codes like that. It gives hint, yeah. Okay. So these are the, this is the figure. I mean, I don't know the exact number. I've just took it from the, from the book. This is for large n and q equal to 2. But still, I would say there are certain constraints, like real world constraints, which have not been taken into account here. So for example, there is a constraint of geometric locality, for example. So let's say when you perform your measurement, let's say your measurements, like the check measurement or stabilizer measurements, they have to act on nearby qubits, like the qubits which are geometrically, like local, like just nearby. And Bravyi and Terhal, I think in 2009, they came up with this bound which applies to a stabilizer code defined on a d-dimensional Euclidean lattice with geometrically local checks. And they said that the small d, the distance on such a lattice that you have, will be upper bounded by small n to the power 1 minus 1 by d. So I can take d equal to 2, for example, and then it will go like order root n. So this tells you that in surface codes, like, or let's say Tori code or whatever, like, surface code, for example, like, I mean, we have, like, I mean, certain sense optimal scaling of, distance here. But later, I mean, there is no encoding rate here. So they also managed to put encoding rate here. And this code, like the Bravyi, Poulin, Terhal bond, applies to wider class of local commuting projector codes. And basically a stabilizer code is a special case of that. Because, I mean, there you definitely have like commuting projectors, yeah, local commuting projectors. And here you have KD encoding rate times small d 2 to 2 by d minus 1 has to be n. So let's say, if you take capital D equal to 2, it becomes KD square equal to ON, right? So if you take your K equal to constant, then D can go maximum square root n. And that's what you have in Tori code. So Tori code is optimal. But if you take K equal to order n, D equal to order n for encoding rate to be constant. So let's say we wanted, right, for the good codes K by N, we wanted to be constant, it's a C1, and we wanted D by N to be constant C2. So K is order N, D is, let's say, order N. If you want that, obviously Gilbert Varshamov bound says that such codes should be possible. But if you put it here, these numbers will be K is equal to, let's say, some N, C1N, and D square is C2N square, which is, like some C1, C2N cube. And this is not upper bounded by, some factor called that C4N. Sorry, yeah, C4N. Like this thing does not hold. This thing does not hold. So this is not possible. This is not possible, this is not possible for, when you put the locality constraint. So good codes are not possible with locality constraint. Like you cannot get a surface code or something, which has a constant encoding rate and constant distance rate, even if it is allowed by Gilbert Varshamov. So what do we need? You need non-local interactions. And that was all the business of, people trying to put as many non-local interactions as possible and trying to get, these good quantum LDPC codes, which I will talk in the next session. So like this, it's good quantum. So this motivates, to look for some of the interesting constructions and so on, which I will discuss in the next session. So I hope you can appreciate, like we talked about 3 bonds, like there was 2 upper bonds, like Singleton bond and Hamming bond, and 1 lower bond, which was Gilbert Varshamov bond. And then there is a bond coming from, geometric locality. And that basically rules out, let's say, good codes which are allowed by Gilbert Varshamov bound. And hence we had to go beyond. We need non-local interactions. Okay, so still I have like 15 something minutes. So I was thinking of, maybe, yeah, I thought if I will have time, I will cover it. So it seems I have some time, so I will cover it. So but still, like, these bonds are not tight. So you can use tools from optimization theory to give even, more tighter bonds. And there are some methods based on, let's say, linear programming or semi-definite programming, which can give you tighter bonds. So let's try to, look at these bonds, like. So for that, we need to define a few kind of enumerators, like, weight enumerators and so on. So let's say, what is a weight enumerator? Like, an important concept here. So weight enumerator is defined in this manner. So let's say pi be the projector onto the code subspace of some small n k quantum error correcting code. Then you can define this number A. I won't go into detail because I don't think we have much time, but I want to get to the point where I can show you that what is this optimization that you do that gives you, that rules out certain kind of codes, for example, which gives you tighter boundaries. So weight enumerator of this code Q is basically a degree n polynomial, which has these coefficients Aj defined in this manner. For a stabilizer code, this has a very simple meaning. It says Aj is basically, or basically it counts how many stabilizers are there. So it counts the size. It counts the size of the set of stabilizers which has exactly weight J. So Aj is basically, you have to count all the. So you have to create a set M. So you have to create a set. So this is a set which has weight M stabilizer. Weight of M is, sorry, weight J stabilizer. So weight of M is J, and you take all such stabilizers, and whatever is the cardinality of that set, you call that Aj. So it's a number. So let's say you count how many stabilizers have weight 1, how many stabilizers have weight 2, and that will be like A1, A2, A3, A4. So you get these numbers. Those numbers you feed in here and you will get a polynomial. And that polynomial is called weight enumerator polynomial. Okay. So you understanding like what this AX is. Dual weight polynomial enumerator is also defined in the same manner, with the difference is that now you count, you don't look at the stabilizer, but you look at the normalizer of your stabilizer. So that is your dual weight enumerator. And I just wrote here what is normalizer and centralizer, what it needed. And in fact, you can relate the normalizer, the weight enumerator and dual weight enumerator using a couple of theorems. So there is something called quantum Mac-Williamson identity, which relates how the weight enumerator and dual weight enumerator are related to each other for a code. For a valid code, this is how they are related. You can also define another object called shadow enumerator. And that also is related to your, like your weight enumerator in some manner. So there is a bunch of constraints coming, and all the constraints are basically linear that you can write. And there is a feasibility problem that you can solve. And let's say, given a parameter, there is no point in the feasible set, then you rule out those codes. So that code is not possible. And that can give you a, like, I mean, it obviously it will be lot of computation, but it can give you a more. And then recently, I mean, there was a SDP bounds on quantum codes, I think, which was a talk at also Asia Pacific Error Correction Seminar Series, which one can look at. So I hope I managed to convey, I mean, what I wanted to convey. And yeah, so I think there was this question about the odd n case, like we were talking about, right? N minus 2. So I think you can take n equal to 3, and you can show that 312 code does not exist. Like this code is not possible using this linear programming method. Like this code is not possible. Yeah. So I think that's it. I hope this was like this made. If there are questions, please ask. Yeah, please unmute and just ask.
Yeah, talking about having bound, that's basically like saying that we can our number of errors uh, cannot go should remain in the space. We cannot violate the the size of the space, right? Uh, in a sense, like this the sphere, it cannot go. How do I put it? Um, so the number of errors that occur, they should be separate because of the nil Laflamme, and they should not violate the size of the space. Otherwise,
Maybe you mean, like here we are counting, right? So we are saying that if they are orthogonal, then this has to be 0. Then this ESI need
yes,
is 5 or orthogonal. So let's see if I start with a bunch of psi I which are bases, then ESII for all ANI are linearly independent. And
yes,
and then you count number of errors, and you count, like number of basis elements, and you say that, their product has to be upper bounded by size of the space.
yeah.
Yeah,
So
yeah.
in case of degenerate codes, uh, I mean it has not been proven, but what I'm asking is, since the errors are just mapping to the same syndromes back, uh, they have to stay in the same space, right? Otherwise, they will simply it will become a logical error if they leave the space.
Yeah, I don't know. I mean, like, when one has to think about it. I mean, I cannot comment. I mean, yeah, it's more of a. I mean, one has to look at what people have tried and so on. I mean, also maybe I need to think more
Okay.
about that. Yeah.
Maybe I'll take it up in the Discord.
As Krishna, thank you, Kishor, for a very nice introduction. So I'm wondering, do all these bounds apply for all quantum error correction codes, or also for, let's say, approximate error correction code, or is it just for really exact quantum error correction?
Yeah, so that's a good question, right? I mean, so let's say, I think if you change the, game. So for example, you allow for approximate code, so their Neal-Laflamme condition might be different, right? I mean, or and so on. So I think one can get different bounds by looking at, different kind of Neal-Laflamme to start with. Yeah. Yeah.
Okay, so if there is not any other questions, so we stop here, right? Okay. Thank you, Kishore. It's a very pedagogical tutorial. Thank you, everyone, for coming here. And for the answer, for one of the answer that